Welcome back to ECE 320A. We are now beginning Unit 4, which moves us into Chapter 12 of the textbook, and it also starts us in a new topic, which is Laplace transforms, and you will have homework number 4 due at the end of this unit, and that will then be a part of exam number 2, which will also include unit number 5. In this video, what I want to do is simply define the Laplace transform and illustrate what results when we apply the Laplace transform definition to a unit step, and then we will look at what happens if we actually delayed the unit step and took the Laplace transform of the delayed unit step, and then we'll just generalize that result to a generic waveform or function or expression in time and show what that looks like in the frequency domain. The Laplace transform now is a way to help us solve problems, and in particular in this class, electric circuit problems, by converting time domain problems into the frequency domain, and we will learn that that will allow us to convert differential equations into algebraic equations, and solving those algebraic equations in the frequency domain will be a little, I think you will find, a little cleaner or a little easier to process, and then we will learn how to bring those frequency domain expressions back into the time domain, so that essentially we now have the complete solution of this differential equation by a Laplace transform technique. In order to do that, we need to define the Laplace transform and what it is doing, but again, it's a simplifying transformation, and it's allowing us to go from one domain, which is a time domain, into the frequency domain. And now if you wanted to think about it, a lot of times I'll be dancing around in the classroom and I'll be saying, okay, now we're in the time domain, and then I'll run over to another side of the classroom and I'll say, let's move into the frequency domain. And that's maybe what you need to be visually thinking about, because we want to be able and comfortable to work not only in the time domain, which means differential equations, but what happens when we now move those into the frequency domain, and now we're working on a different side of the classroom, we're in a different domain, we're in the frequency domain, but if we can make the connection and feel comfortable working in the time domain and the frequency domain and going back and forth, you will have progressed a large distance in your education as an electrical and computer engineer. Let's now look at what it means in terms of an equation. And we will focus on a single-sided Laplace transform, which means that we are focusing our attention on the time horizon that begins at 0 and then goes all the way up to, you can't really reach infinity, but goes to infinity. So now we're looking at positive time waveforms, or waveforms that are defined over this non-negative argument of time, t. And if we can now Laplace transform, think of this little f of t as some function of time. We now scale it by a complex exponential, e to the minus st. So we're now scaling this, and we're making this entire integral argument, f of t e to the minus st, integrable, so that we've now collapsed all of this time domain information, whatever f of t is doing with respect to time, we've now boiled it down into a new expression in terms of this complex frequency variable s. So we're now extracting, or we're compacting, or we're collapsing all of this time horizon information of f of t from time t equals 0 up through and to infinity, and now we're packaging it as a collection of frequency domain information, which we will then call capital F of S. And that's what we want to do now, is become comfortable moving from the time domain over here into the frequency domain F of S. And once we can do that, once we become comfortable doing that, we will be very well on our way to becoming electrical and computer engineers. A lot of times we may not want to be writing out this integral expression, and for that reason the notation that we might then use is we might say capital F of S. That now says, oh, we're in the frequency domain S. S is a complex frequency variable. S has a real part and an imaginary part, so you can think of now you're playing on this two-dimensional plane that has a real part and an imaginary part. That's now the argument of our Laplace transform expression, and that arises out of this infinite expanse waveform in the time domain, little f of t. And we'll just say script L of f of t. That means utilize this particular expression, meaning weight that time domain waveform by this complex exponential e to the minus st, integrate that from t equals 0 minus, so now we're starting just to the left of the origin in time, or we're including all of time t equals 0 in this Laplace transform expression and finding capital F of S. Let's see what that might look like for a particular waveform, and let's not get too fancy in this first example. Let's just deal with a unit step. That means that we now are looking at the time domain waveform that is 0 from minus infinity up to time t equals 0 minus. At time t equals 0, we kick on, or when the argument of u of t becomes non-negative, then that waveform turns on or assumes a value of 1. And it's 1 until infinite in time. So we want to now Laplace transform this signal. Capital U of S, we're now converting from time domain, which is usually lowercase, to frequency domain, which now the notation will be capital expressions. And now we have capital U of S is this script L of U of t. That says the Laplace transform of U of t. That's defined to be this integral from 0 minus in time all the way up through infinity, or to infinity, u of t e to the minus st dt. What does that look like? Let's see if we can calculate it. So now capital U of S is going to be this integral from t equals 0 minus to infinity, and we want to know what is u of t as a function of time from 0 to infinity, and we've picked one that's pretty easy. It's constant. It has a value of 1 from 0 minus all the way up through infinity, or to infinity. E to the minus st dt. Now we simply need to integrate e to the minus st. Don't worry that s is a complex variable. Let's just treat it as a variable. We're integrating with respect to time, and in this case we have this negative exponent. We now have minus 1 over s e to the minus st, and we evaluate that at the lower limit and the upper limit, and again we're evaluating that when time is equal to 0 minus and infinity. Or we now have minus 1 over s That's independent of time. Evaluate e to the minus s at infinity. So now we have infinity minus e to the minus s 0 minus, and that's now going to produce the Laplace transform of a unit step, or u of s is now minus 1 over s, and s we're assuming now is a variable, but we're raising e to the minus s infinity, so that now vanishes since we're raising something, or we're saying 1 over a very large quantity. This now becomes 0. E to the minus e to the, and now we have 0 times s, so that annihilates the exponent, or we have minus e to the 0, which is now 1. Or we have minus 1 over s times minus 1, or that's now 1 over s. This is now the Laplace transform of a unit step. We've now boiled down this infinite horizon signal in the time domain from 0 to infinity, and we've collapsed that down into a frequency domain expression that is a function of this frequency variable. It has one, let's say, polynomial in s in that formula, a constant numerator, and we're dividing by s this complex frequency variable. So the Laplace transform of a unit step is 1 over s. Let's now take that up a notch and look at what happens if we Laplace transform not the unit step, but a delayed version of the unit step. And in this case, the argument of the unit step, we want to know when does that become non-negative. Well, now we're saying when is t minus t sub 0 non-negative. That's going to occur if we now solve that for t when t is greater than or equal to t naught. And when that argument of that waveform, of that step, unit step, is non-negative, that's when it assumes a value of 1. So t greater than or equal to 0 is the time when this waveform is non-zero, or when it equals 1. And that's what we're showing here in this picture. We're saying up until time t equal t naught, our waveform is 0, and after t naught, it now assumes a value of 1. Let's now see if that changes anything when we try to Laplace transform this delayed unit step. Now we can say, let's now Laplace transform, so that's script L of little u of t minus t naught, or plugging that into the definition, that's when t goes from 0 minus up to infinity of u of t minus t naught, e to the minus st, and we integrate time away and are left with an expression involving only the complex frequency variable s. And this looks a little bit messy because now we have u of a little bit more involved argument, t minus t naught, e to the minus st dt. It'd be nice if we could boil this down to where we knew when that was 0 and when it was 1. So in order to do that, let's do a change of variable. Let's go ahead and let tau equal the argument of our unit step. Again, t naught is just a fixed constant. It's going to be given, and it says, okay, at t naught, that's when the unit step kicks on or turns on. You could think of this as a switch. If t naught is constant, then if we look at the differential of tau, or d tau, that's going to equal dt. Since the t naught is constant, it's not changing, dt naught is 0. So with this assignment, we can now replace t and t naught with something that hopefully will give us an expression that we're more comfortable integrating. We can now solve this for t, and if we do so, we can see then that t is just tau plus t naught. We are integrating in this integral of this delayed unit naught from t equals 0 minus. If we plug that in to this relationship, then we see that tau is equal to minus t naught. And we are also going to want to know what happens at the upper limit of this integral, which is infinity with respect to t, or time. If t goes to infinity and t naught is a fixed constant, tau also will go to infinity. Now we're hoping that this allows us to rewrite this Laplace transform expression for this delayed unit step into something that's a little easier to evaluate. So now instead of going from t, we're going from tau equal to minus t naught up to tau going to infinity. But now we've defined, t minus t naught to actually be this new variable tau. So we're trying to clean that up so that we're more comfortable with what's going on. We now have u of tau, and that gets scaled by e to the minus s, and now that was multiplying by t, but t is tau plus t naught, and now instead of integrating with respect to t, we're integrating with respect to tau, and we just convinced ourselves that dt is the same as d tau. Now what we want to do is actually remind ourselves of how we can separate this exponential. When we have this summation in the exponents, that means we can actually have a product of exponentials. If we factor this as e to the minus s tau, e to the minus s t naught, now we have something in the argument of our integral that doesn't belong, or is not a function of tau, so that we can now factor out e to the minus st naught from the integral, and we're left then with this integral from tau going from minus t naught to infinity of u of tau e to the minus s tau d tau. And that now looks very familiar, except the lower limit, but we can get around that. We now have e to the minus s t naught. Let's now break this up into two parts that allow us one of the parts to look like what we've already worked with. So now let's say we're going from tau equal to minus t naught up to tau equal to 0 minus u of tau e to the minus s tau d tau plus an integral from tau equals 0 minus to infinity of u of tau e to the minus s tau d tau. And what I hope you see is that this looks very familiar. That's just what we integrated before, only we had the variable of integration being time and not tau, or t and not tau. But what's happening on this left-hand piece of this broken or separated integral? Now we can look at u of tau. When does that evaluate to 1? Well, that evaluates to 1 when tau is greater than or equal to 0. But look at the limits on this integration. They are from negative t naught up to 0, and during that interval of time, or interval of tau, this is 0. So now we have this integral of 0, the whole thing now. That entire integration is going to contribute nothing to the overall result. Now we can write down the answer. Essentially, we have e to the minus s t naught. T naught is fixed. S is this complex frequency variable. In square brackets, we have 0 plus, and we already have evaluated what's highlighted in yellow. That ended up just being 1 over s. That's just the Laplace transform of a classic unit step. Or we now have the Laplace transform of a delayed unit step is now e to the minus s t naught over s. That's now the Laplace transform of I'll use the curly braces, although my curly braces, I am challenged to write those very cleanly, but this is now a delayed unit step, delayed by t naught, and you can see that it differs from an undelayed unit step by this additional factor or scaling amount, e to the minus s t naught. T naught is constant. That's when we turn on the unit step, and s is our complex frequency variable. So now, if we had a conventional unit step that started at t equals 0, that would have a Laplace transform of 1 over s. By delaying that unit step, a delayed amount of t naught, we now scale 1 over s with e to the minus s t naught. And that particular result for the unit step of a delayed unit step can actually be generalized. And in general, if we take an arbitrary waveform, f, and delay it an amount t naught, then that's the same and we want the Laplace transform of that. We can find that by simply scaling the Laplace transform of f of t by e to the minus s t naught. What we showed in particular for the unit step now holds in general, or we can now say that if you now delay a waveform f of t by an amount t naught, then its Laplace transform is going to just be a scaled version of the original Laplace transform f of s, and it will be scaled by e to the minus s t naught.